All right, folks, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 360 control system. And today is our lecture 27. Should be the very last lecture for this semester. And today we will continue to try to finish the from the given state space representation to find the corresponding equivalent transfer function in frequency domain. Okay. So last lecture we have talked about the formula we're gonna apply to solve such problem. Okay, and first of all, you need to realize the given state space representation here looks like this, right? So you need to be clear. This. Therefore, you are fully realize A, B, C, D, 4 matrix, or say 4 matrix and or vectors. Where are they? Okay, where to find them, right? Because the given state space is like this. Rather than directly telling you who is A, who is B, who is C, who is D, right? You need to identify them yourself. After successfully doing that, you go ahead to apply this formula. And inside of this formula, the key thing is here. S is the S we have been using and play with through the almost the entire semester, and times the I, which is identity matrix, okay? And equals to what? S times I equals to a matrix with main diagonal of entry S and 0 elsewhere, right? This is SI value, or say SI matrix. And this matrix is subtracting the matrix A. Okay. And then you need to find the inverse matrix of this SI minus A. Okay, this is probably a little bit hard. Okay. After this inverse matrix, you are left times C and right times B. And then at last, don't forget to add A. To add D. Okay, to add D. So this is the procedure, and let's go through examples to see specifically how we do it. Okay. Assuming we are given a state space as below, just find the frequency domain transfer function. Okay. So the given state space is like this. X equals to matrix 1, 2, 3, 4 with entries of plus 5, 6, U. The Y here equals to 7, 8, X plus 9 times U. Well, of course, apparently I randomly designed the numbers and the entries of the vector and the matrix to just to show you the procedure, how we should do it, Okay. And as I said, this guy is A, right? This guy is B. This guy is C. This is D. Okay. At the very beginning, you need to understand who are which, right? Who is whom. Okay. After identifying A through D, you go ahead to do what? Obviously, you want to begin with SI minus A, right? You want to begin with this to see what matrix this is. First of all, what is your expectation on the resultant matrix? What's the dimension of it, of this guy? What's the dimension of it? What are you expecting? 2 by 2. Very good. Noah is right. Okay, it's 2 by 2. So S times I, obviously, you end up with this. Right? This is S times I minus A, which is 1, 2, 3, 4, equals to a 2 by 2 matrix. So first entry is what? Just equals to the subtraction between two entries in two matrix, right? S minus 1. The entry here is what? -2, right? -2. Entry here is what? -3. Entry here is S minus 4. Right? They're very straightforward. Yeah, you have two matrix with exactly same dimension, then the resultant matrix has the same dimension as them. And also each entry here is actually just equals to the subtraction between the two matrix here, right? So element-wise subtraction. Okay? Element-wise subtraction. And after that, we start to find what? Inverse matrix. Inverse matrix. And how to find the inverse matrix? Anyone knows how to find the inverse matrix of this guy? What do you guys learn from math class? Transpose? Yep, a part of it, correct. Any more details? Actually, this is a 2x2 matrix, right? So we don't have to go through that complicated transpose procedure. Okay, that's a very complicated procedure. So we have a formula to apply. Okay, assuming we have a 2x2 matrix like this, the inverse matrix of this, obviously, generalized 2x2 matrix is what? Anyone knows actually? What is the inverse matrix of a 2x2 matrix? Any impression? Flip main negative other diagonal. Well, sort of. Yep, close. Noah's answer is actually close. First, you have flip the main diagonal entry. Main diagonal entries are A1 and A4. You flip them. And then what else? To the A2 and the A3. Give them negative sign. A negative sign. Here we go. And be very careful, as Noah mentioned here. It's not the end, okay? We're not done yet. This matrix need to divide it by a determinant. Divided by a determinant. Whose determinant? Nothing but the A1, A2, A3, and A4. The original matrix determinant. Okay, original matrix determinant. And therefore, this equals to what? Equals this, right? So determinant here, how to calculate this determinant? 2x2. A1, A2, A3, A4, what's the determinant? Good. Okay, good. A1 times A4 minus A2 times A3, right? So this is in the denominator, so 1 over the denominator. And what you want to do is not times this factor into the matrix, but keep it outside. Here we go. Now this is the result of the 2x2 inverse, 2x2 matrix inverse matrix. AD minus BC means nothing but A1 times A4 minus A2 times A3. Okay. And this is the kind of formula we can use to sort of calculate the 2 by 2 matrix inverse. Okay, inverse. The easiest case. Okay, easiest case. It's not a formula could be applied on any other dimensions. Okay, be very careful on this. So because of this formula, let's do this, right? Let's do this. So what have we got? Basically, determinant 1 over the determinant, right? 1 over determinant times matrix what? Flip the main diagonal and then give the negative sign to -2 and -3, and then we end up with this, right? And the determinant is just as simple as -1 times s minus 4 and then -6, right? Any questions? Of course, feel free to just like extend this polynomial. So it ended up was s squared minus 5s minus 2, right? This is inverse matrix. And once again, don't try to times this guy into each entry. And that's gonna make the matrix more complicated. Okay? That's not something necessary. Okay? We don't want to do that. We don't want to do that. Keep it as a mutual factor outside of the matrix. All right. After having this Si minus A inverse matrix, let's take a look at the formula. What we have: C times left times it, and then B right times it, and then plus D. Right. How about I give you guys 3 minutes to try this off? So you have this Si minus A inverse matrix like this, and then you left times C, right times B, and then plus D. Go ahead. Give you guys 3 minutes. Try this out. Of course, meantime, consider one thing. Your result of this formula, given formula here, what's the dimension of it? What's the result dimension of this matrix operation? Very good. 1 by 1. Okay. Very, very good. Very, very good. 1 by 1. Okay. Why 1 by 1? Well, no matter how complicated your transfer function is just one single entry. Does it make sense? It's 1 by 1. Okay. No matter how complicated, no matter how long the polynomial in the numerator or denominator is. Okay, it doesn't matter. Yes, 1 by 1 result. Good, very good. And if you consider the dimensions of the matrix A through D, then you should end up with the same answer. Okay. All right, let's see the detailed calculation here. So we go ahead with the we can continue from here. So the transfer function is just a C. Who is C? 7, 8. Left times onto this inverse matrix, which is this. Right times B, 5 and 6, plus D, which is 9. Right? This is the equation. This is the equation. And then how we do it? And once again, we put this factor, this polynomial factor out. So 7, 8 times this 2 by 2 matrix what is it? What is it equal to? So 7, 8, which is C times this SI minus A inverse matrix. What is the resultant matrix dimension? Very good. It's 1 by 2. Okay, 1 row, 2 entries. Here we go. This is the result of C time left times onto SI minus A inverse. And if this is clear, and then it should end up with this. Right? So 7 times S minus 4 plus 8 times 3. Okay, this is the first entry. Second entry here is equal to 7 times 2 plus 8 times S minus 1. Right? This time 5, 6. And what have you got? What's the dimension of this product? What's the dimension? One by one, correct. Okay, no, it's correct. So eventually this equals to, if you do everything correct, it should end up with this. $83S plus 16. And then further, you can put everything into one fraction, which is a ratio, kind of a polynomial ratio, right? Denominator, of course, definitely s squared minus 5s minus 2. A numerator should be, if everything correctly calculated, I should end up with this. Okay, 9s squared plus 38s minus 2. This is actually algebra of the matrix. Algebra of the matrix. So take a look to see any questions you have. Anything? Yep. Now you got to do some exercise. Okay. Do obviously repeating this example, and also I give you another example and solution for you to do after the class. Okay. Example 5. So the given state space is like this. Okay, this is given state space. And then find the transfer function. Find transfer function. And the solution here I'm giving you is actually transfer function is equals to, is also a ratio, of course, equals to 10 times s squared plus 3s plus 2. Denominator is s cubed plus 3s squared plus 2s plus 1. Okay, this is the correct solution. And then you can do the calculation yourself. Try to reach the same answer, which means you're okay with it. And this is the given state space, and find the corresponding equivalent transfer function in frequency domain. So the other way around. Because before this, we learned given transfer function and find state space. This is the other way around. Now let's talk about the very last thing of this module, and obviously also this course. It's called signal flow graph. What is signal flow graph? To explain this, we want to think in this way, okay? So in frequency domain, our model is what? Transfer function, right? A transfer function. This is our model, right? And don't forget, we also have what? Block diagram, right? By block diagram algorithm, we can reduce the complicated block diagram into one single total transfer function. Remember that? That's one of our module. And the block diagram is trying to do what? It's trying to represent the system, visualize the system. Okay. So different way, alternative way to represent the model of the system. Following this idea, so in time domain, our model is state space, right? Correspondingly, we also have a graph or say diagram thing to visualize the system. It's called signal flow graph. So obviously the key is the given block diagram, we are able to find the transfer function. Okay? And here, what we're gonna do is given state space, try to find signal flow graph. Okay, this is what we're gonna do. This is what we're gonna do. Okay. So let's see how to directly. That's just a how to sketch a signal flow graph for a given state space representation. Right? How to do this? It's actually fairly easy, but once again, you do need exercise, okay, to become familiar with it. So the first step is actually you're place signal nodes in such order. Here, signal nodes. So signal and the variables are represented by nodes. Okay, we will see by example. But this order you need to remember. This order is very important. What order? You place the input signal at the left end, okay, followed by derivative of SVN. Who is SV? Anyone still remember? Who is SV? In state space representation, who is SV? Of course, we have always more than one SV, but who is it? State variable. Very good. Okay, state variable. You have more than one state variable, so you're placing the derivative of a very last state variable, which is named as state variable n, right? And then followed by state variable n, followed by derivative of state variable second last one, which is obviously n minus 1, right? And then followed my state variable n minus 1. So on and so forth. Obviously, you are going to place all of the state variable derivative and state variable in such order, and all the way up to derivative of state variable 1, followed by state variable 1. Right? And at the right end, which is the end of this order, is the output. This is the order. You need to remember this order. This is how we build up the signal flow, following certain order. Left begin with the input, right ended by output. In the middle are derivative of the state variable and state variable. And after doing this, second step is to interconnect all signal nodes based on the coefficient in SE and OE. And of course, who is SE, who is OE? Yep, here we go. Kevin is right. The state equation and output equation. Two steps. First one is following certain order contained by this red box. Okay, following this order to place all of the signal nodes. Second is interconnect them. How? Based on the given state space, which consists of SE and OE. Right? These are the two steps. Fairly easy. Let's see the example, how we really employ this procedure. Okay, so example 6. Find signal flow graph or state space below. First of all, you got to realize this is the state space, and obviously these two simultaneous equation is SE. This guy is the OE. How many state variables and who are they? Very good. Okay, Kevin is following very well. Okay. Because going back to the procedure here, you're placing those signals, placing the state variable derivative or state variable themselves, right? So of course you need to identify them first. Who are they? State variables. State variables x1 and x2, right? What do you mean by derivative of them? Derivative of state variable means obviously x1 dot and x2 dot. Does it make sense? You're gonna place them into our paper. Then first of all, you need to identify them, right? Besides, input is what? Output is what? Right? These two are very easy. Input is just a U here. Output Y here. Right? After identifying them, I think it's ready. Ready. So let's do it. Okay, let's do it together. How to do it? From left to right. Okay, from left to right, you are placing input first. Okay, input, we use a node, kind of circle to represent input, and then write input U below it. Moving towards right, and then followed by another circle, a node representing what? Derivative of a state variable n, right? Who is it in this particular example 6? Who is it? x2 dot. Very good. Okay, very good. Alex is right. Does it make sense? This is the very last state variable is x2 in this particular example. Followed by whom? State variable n, right? State variable n is whom? x2. We just identified. Followed by second last state variable derivative, which is x1 dot. Followed by the second last state variable itself, which is x1, right? No more, since we only have 2 state variables. So with their derivative, we have 4. Okay. 1, 2, 3, 4. The last signal here is the output y. Done. Including, of course, inputs all the way to the output. In the middle, you have derivative of the state variables, every single one of them, and also state variable themselves, every single one of them. Right? Now you have all of the nodes, signal nodes, established. This is the first step. The first step, placing the signals properly. Second step is interconnect them based on the given equation coefficient. How to do this? You need to go back to the given state equations and output equations and read them carefully. For example, first. Okay. X1 dot equals what? X1 dot equals to 2 as a coefficient times x1 plus 1 as the coefficient times x2. What does it mean? x2 1 dot is over here. Okay, x1 dot is over here. So this guy is contributed by 2 times x1. 2 times x1. This is how we label it. It's going back, right? This signal is going back because x1 is on the right-hand side of the x1 dot. So this is going back. So going back signal, and then you keep it below the horizontal line. If you consider this as a horizontal line, then this is the going back word signal, then, or say operation, then you are going below it. Okay. Give a curve, label the coefficient as the weight. This means 2 times x1 is contributing the x1 dot. Besides, you have contributing from x2, right? x2 is here. x2 is directly going forward with gain of 1. Okay, you definitely can use the definition of the concept of gain. Right? This is moving forward, so you can use along the horizontal line or above it. This is the first equation done. Yeah, first equation done. x1 dot equals to 2x1 plus 1x2. Right? This is how we do it. First equation done. And follow the same idea, we're taking care of the second equation, x2 dot, which is this guy, right? Is equals to what? x1 plus u. x1 plus u. Where is x1? x1 is here. Okay, is another going backwards, right? So below the horizontal line, below the horizontal line, we have a route from x1 towards x2 dot with gain of 1. And then plus u, right? Plus u is moving forward along the horizontal line with gain of 1. This is the second equation done. Second equation done. x2 dot is contributed by 1 x1 and 1 input. Okay, those two ones are gain, right? The gain, obviously the gain. The last, let's take care of the third, which is the output equation. The output equation, y equals what? Y is equals to x1 plus x2. x1 is here. This is easy. It's directly shooting towards y with gain of 1 plus x2. x2 is here, right? Obviously, you can't use the horizontal line here anymore. So you give a curve over the horizontal line with gain of 1 as well, right? This is contributing from contribution from the x2, right, towards y. The last plus 2u, plus 2u. U is here. You need an even bigger curve here with gain of 2 to represent the contribution directly from the input. So we are done with the output equation now. But the last, not the least, remember, between x2 and x2 derivative and x1 derivative and x1, we also have a relation. We want to connect the derivative of the state variable and state variable themselves. And if we are talking about course right direction, then x2 dot to x2, what is the gain here? And from x1 dot to x1 here, what's the gain here? Anyone has any idea here? 0? No. Very good. Excellent. Our Turkey is right. x2 dot is derivative of x2, right? The derivative of a variable towards the variable itself is what? You need to do an integral, right? Does it make sense? If you do integral, you can label it integral like this, right? In the list. But actually, we are not doing. We are not labeling the integral like this. Instead we are labeling the frequency domain transfer function, which is 1 over s. 1 over s is what? 1 over s is the Laplace transform result of integral. Does it make sense? Who is the Laplace transform result for s? Who is here? The Laplace transform result is s. Then what is it in time domain? Anyone knows?
Derivative, right?
Derivative. Here we go. So this is a two basic Laplace transform result to understand. S means actually nothing but derivative. 1 over S is actually integral. Okay. Now we are done. And from this signal flow graph, you can tell along the horizontal line, there is no open, right? No open. But could it be open? Not possible between x dot and x, right? Definitely you need a integral over there in between. But you might not contributing anything towards the x2 dot. That's possible, right? Absolutely possible. And your x1 here might not contribute anything towards the output either, right? So here, of course, possibly open. How about here? x2 to x1 dot. Is it possibly open?
Shouldn't it not be open because aren't they all related to a system?
No. This is absolutely possibly open as well. Your first, yep, Alex is right. So your first derivative of the first state variable, well, might be equals as x1 dot what? 3x1 plus u without contribution from anything from x2, right? So it's absolutely possible. So in other words, it's 0 times x2, right? x2 is contributing nothing towards x1 dot. That's possible. Right? That's possible. So in this particular example, yes, nowhere is open, but it's possibly open. Okay. If this is okay, then let's give you guys some time to try this example 7. All right, go ahead to find the corresponding signal flow graph. I'll give you guys 3 to 4 minutes. Go ahead. All right, let's see the solution together, okay? Obviously, we start to place the signal first. So begin with U, and then the next is whom? Who's the next? X3 dot, good. The derivative of the last state variable, and followed by the last state variable, and then x2 dot, followed by x2, and then x1 dot with x1. And that's it. Right? That's all of the state variables. And of course, at the end is the output. And these are the signals. And then we start to interconnect them. Well, obviously, feel free to populate these three. How about that? Feel free to do this first, right? No way to change, okay? No matter which problem, these three, or, well, depending how many state variables we have, but these integral always true, right? Always true. So feel free to do them first. Second, let's see the first equation here. First equation is x1 dot equals to -2x1, right? x1 dot equals to 2, -2. -2, since this once again is going backwards towards left, so it's below the horizontal line. -2 times x1 contributing to x1 dot, and also we have 1 here, gain of 1 contributing from x2. Any contribution from x3? Nope, right? No. And any contribution from input? No, right? No contribution from x3 and input. Okay. So next, yeah, go ahead.
Would it ever be the same thing to flip the arrow the direction and change the sign, or no? Is that not the equivalent?
Well, you gotta follow this rule. Okay, you change the direction and change the gain. Of course, still equivalent, no problem. Mathematically, it is equivalent, no problem. However, when you use the signal flow graph to do the design and some judgment on stability, which are beyond the subject of this course, you're going to be messed up. You have to follow such way. You have to follow this way. Mathematically, that is equivalent, of course. But without following this rule, the later on design, the analysis going to be messed up.
Okay.
Yep. And this is the first equation. The second equation is x2 dot equals to 0 contribution from x1, and -3 from x2, -3 from x2. And 1 from x3. Any contribution from the input? Nope. Nope. 0. Third equation, x3 dot equals to -3 times x1, right? However, be careful. Okay, when you plot this, you want to have a big curve. You want to have a big curve. The reason is you also have contribution from x2 and x3, which are also moving towards left, right? So x2 here is x3 here is -5. And don't forget you have 1 contribution from the input. So we are done with the state equations. Last, the output equation. So nothing from x1, nothing from x3, and nothing from input. Only x2 is contributing, which is here, contributing towards the output with gain of 1. And that's it. So take a look to see any questions you have. Here I'm seeing Sawyer is asking, what are these graphs for? For analysis, for stability judgment, for design of controllers, especially for judging the stability. We have rule to follow. You can tell the stability from this signal flow graph, but we don't have time for this course to teach it.
Why not use the standard stability from the closed loop transfer function, or sorry, the open loop transfer function? I mean, like when we're evaluating whether or not the system's unstable from the open loop transfer function, uh, why would we want to use this method compared to what we currently have for stability?
First of all, we never judge the stability based on the open loop transfer function. We are judging the stability based on the closed loop transfer function, poles. And this is the first. Second, comparing to that, well, one is frequency domain method, another is time domain. They are theoretically equivalent and alternative to each other. I'll give you an example. If you're modeling a very complicated nonlinear system, which method we want to use? Do you guys know this? To nonlinear system, the time domain, this one, state space, is actually better. It's a better method to design a controller, to judge the stability, etc., etc. If it is a linear system, the frequency domain transfer function is actually more convenient. These two methods, your understanding, correct understanding, is alternative to each other. Okay? For different system, you might choose one over the other.
Okay, makes sense.
How is it to you, Sawyer?
That makes sense. So is the root locus method, because we learned that to find stability, is that more commonly used than these methods?
Once again, if it is an easy linear system and there's no very complicated nonlinear component like the saturation, like the dead zone, nothing like those, then root locus is very good method. And even in digital controls class 460, yes, you're gonna do root locus as well.
So, for example, then this time domain that we're using to model, that can model something like you're saying saturation from inductances, like in a particular circuit, maybe. You can actually model that nonlinear part, not just nonlinear resistive.
Yes.
Huh, okay.
Yep. But actually, my personal experiences, when we deal with those nonlinear components, we are trying to use linearized method. We're trying to linearize those, or separately deal with them, isolated from the rest of the system. But this state space can deal with nonlinear system, very complicated one. Yep. The state space is actually the basic knowledge for more advanced, more than control system course, elective course. 460 still is digital, teaching you how to deal with everything, root locus, transfer functions in Z domain, okay, not in S domain. This is also why I leave this module at last of the semester.